Hey everybody, today surface area and volume of spheres. We're slapping both of those things about spheres in together. So first we did surface areas of different figures, then we did volumes of different figures. Well, spheres, the formulas are so closely related, we're throwing them together into one chapter, one section. A little bit of vocab about what is a sphere, and don't think any of these are going to knock you over. They're fairly straightforward. Okay, I'm sure you can already picture some of this. What is a sphere? What's the center? What's the radius? What's the diameter? What's the circumference? All right, so let's just show you. So a sphere is the set of all points that are equally distant from a given point. Here, our given point is what we call the center of the sphere. And in this case, it's a little red dot. Well, every point going around in the plane of the board or into the board or out of the board gives us a perfect ball shape, a sphere, a spherical object that's coming out in 3 dimensions, out of the screen and into the screen and around the screen. But every point that is the same distance from that center is on the sphere. Now, a radius would be a segment that has one endpoint at the center and one endpoint on the sphere. The green line here would be a radius. A diameter would be a segment that has endpoints on the sphere, so goes from one side to the other to the sphere, and also goes through the center. So just to make sure we understand again, notice that I could draw a picture of another diameter. If I chose to go from this part of the sphere through it to the opposite side, now again I'm going front to back, but that's also a diameter, right? But it would have the same length as the other blue one that we started with. Okay, so diameter goes from one side to the other, goes through the center of the sphere. Of course, there are infinite numbers of radiuses, infinite number of diameters. Okay, there are also infinite numbers of ways to cut this circle into cross sections. But anytime you do, anytime we pass a plane through it, anywhere we pass the plane, we will cut it, and the cross section would give me a circle. Okay? Now, I know that's an ugly drawing, but we'll just kind of go from there. If we cross a plane, cut it in half through the center of the sphere, so we cut it so that the plane crosses through the center of the sphere, then we've cut it into the biggest possible circle that we can make. That's called the great circle. So, if you take a cross section where the center of the circle formed is also the center of the sphere, you have a great circle. Okay, and of course there's not just one. Once again, if I cut it this direction, okay, I would form a great circle that contains that center around that way. But it's harder to draw, so we're just only going to look at this one great circle we have here, realizing again that there are an infinite number depending on how I pass the plane through the sphere. Any great circle, though, divides the circle into 2 equal halves, 2 hemispheres. All right? Now, know also that the circumference of a great circle would be what we would call the circumference of the sphere. Okay, so the circumference of the sphere is the same as the circumference of one of its great circles. Nice typo right there. I'll have to remember to fix that. Okay. I think that covers all the vocab. Let's get you into your formulas. It's as easy as it gets. For any sphere, the surface area is 4 pi r squared, and the volume is 4/3 pi r cubed. That's all we need. Let's show you how to use it. So, if you were to travel around the world at the equator, you'd have to go about yay far, 24,902 miles. Using that information, can you figure out the approximate surface area of the Earth and the approximate volume? Here's your chance to pause it. See if you can come up with the answers. All right. So, the equator would be a great circle. So its circumference, this number right up here, its circumference would be the circumference of the Earth. So let's find that circumference, plug it in, work backwards to find the radius of the Earth. So, dividing by 2 pi, I find that the radius of the Earth is 3,963.3 miles. So again, took circumference and just divided it by 2 pi, we find the radius. Good. Next, we're going to use that radius to calculate the surface area. 4 pi r squared, plug in r, we got our surface area. We're also going to use it in this formula for volume, 4/3 pi r cubed. Plug the radius in for r, cube it, multiply by pi, multiply by 4, divide by 3. We have our volume. Good. That's how it's done. Next example. So a certain sphere has a volume of 5,000 cubic meters. What's its surface area? Okay, so pause it. Here comes the answer. We, of course, are going to have to use the volume formula and work backwards because now we're given the volume. We're going to need to find the radius so that we can solve it, so we can figure out, use that to solve for the surface area. Okay, so we'll plug in volume, find radius. Here we go, plug in volume. Now, if we multiply by 3/4, this goes away, and that gets reduced to that. If we divide by pi, that goes away, and 3750 changes to 1193.7 equals r cubed. Now we take the cube root of both sides, and we find that our radius is 10.6 meters. We're going to use that, 10.6 meters, plug it into the surface area formula, and find that our surface area is about 1414 square meters. Now, let me show you how to do that on a calculator, just in case you weren't quite familiar with how to do it. Okay, so on, clear. So, we're starting with our 5,000 right there. And I said I'm going to multiply it by 4/3. Or sorry, multiply by 3/4. Several ways to do it. Okay, we could do multiply times 3 over 4, all in parentheses. And there's our 3750. We could also take our 5,000, do it this way, times 3 divided by 4. And that would work. Or we could take our 5,000, even do it times 3, enter, divided by 4, enter, and there's our 3750. Okay, now we're going to divide that by pi. So I divide by second with the pi button, and there's my 1193.7. Now, to take a cube root, there are two ways of doing it. Here's the first way. I'm going to push this little key that says math, and then go down right here to this number 4 option, right? That says the cubed root, and then in parentheses, so I select that, and I put my 1193.7. Okay, so hit math, choose the cube root button, enter your value, and then push enter, and you get our 10.6. Okay, now the second option, I usually don't like to do that because I try to go faster. When I get that 1193.7 and I want to cube root it, I remember that a cube root is the same as taking something to the 1/3 exponent. So if I take that number and I raise it to a fractional exponent to the 1/3 power, it's the same as taking a cube root. So either of those choices work. Use the math button to get the cube root function, or you take something to the 1/3 power and you have a cube root. Okay, so that's where we got that 10.6. We plugged it in here now. Actually, we squared that number and multiplied it times 4 pi. And there's our 1414. All right, so that's how you use the calculator to do those. Hope that helps some of you. Okay, one more problem. Let's find the surface area and volume of this composite figure. I've got a cylinder and I've got a hemisphere. So, pause it, give it a try on your own. Here comes our answer for surface area. Ready? Okay. Looking at a hemisphere, the surface area, well, normally the surface area of a sphere is 4 pi r squared, right? But since it's only a hemisphere, I'm only going to use half of it. That's why the half is right there, okay? Because it's a hemisphere. So 4 pi r squared times 1/2, okay? So my radius is 2, square it, I end up with 16 pi, take half of that, and I get 8 pi for the surface area of the hemisphere. Now, be careful with your cylinder, because the cylinder does not have this top. This area right here would be normally part of our calculation for the surface area of a cylinder, but it is not on the surface of the figure, so I can't calculate it. I'm only going to use the lateral area of the cylinder and one base, the base that's on the bottom. Okay? I am not going to use both bases. So, when I calculate the cylinder without a top on it, instead of using 2b, like I normally would here, I'm only using one base. Alright? So, the area of the base then, for crying out loud. Just fix this. I must have forgotten to save it. Aish. So, let's make this change here real fast. That is incorrect. It is not. The area needs to read pi r squared, right? Okay, so a base is pi r squared. The lateral area is 2 pi rh. When I plug this in now, let's fix this again. It is not 2 pi r, it is 2 pi r squared, or pi r squared instead. Okay, fix that. It is pi r squared plus 2 pi rh. Still comes out to the same answer. That's 4 pi. This comes out to be 10 pi. We end up with 14 pi. Now we add the two components, the 8 pi from the hemisphere, the 14 pi for the cylinder without its top, and I get 22 pi. All right, so that's how we would do that. For volume now, we're going to use for the hemisphere the formula for volume, 4 pi r cubed, but only half because it's a hemisphere. Okay, plug in 2 for the radius, and we end up with a fraction this time, 16 thirds, right? That's 8 times 4 is 32 sixths. 32 sixths reduced to 16 thirds. For the cylinder, now we don't have to worry about whether it's got a top or a bottom. The volume is still the volume. So base times height. Pi r squared h times the height. The volume of the cylinder is 10 pi, which I'm going to use the fraction form here later. You just see how I changed the 10 into a 30 over 3. Then I'm going to add the two volumes together. 16 thirds pi plus 30 thirds pi gives us 46 thirds pi to leave it in exact form, and then it calculates out to 48.2 if we do it that way. So, hope you had fun with that, and I will see you later.